Founded in 1937, STEAG has been a pioneer and trusted brand in efficient, reliable and future-ready power solutions for over 8 decades. Headquartered in Germany's industrial heartland Essen, STEAG has developed, commissioned and operated over 11 gigawatt of thermal and renewable-based plants. Beyond owning and operating power assets, STEAG's expertise spans the full energy services value chain. Engineering, operation, maintenance and cutting-edge digital solutions. From high-efficiency hard coal power plants to combined cycle plants, from CFBC technology to solar fields, wind farms and battery storage, STEAG has enabled cleaner, more resilient energy systems in over 80 countries. In 2001, STEAG brought world-class German expertise to India by creating a wholly owned subsidiary, STEAG Energy Services India, with the motto, "Quality in everything we do." STEAG India has grown to operate and maintain over 6 gigawatt of coal, oil, gas and renewable-based power plants. The company delivers end-to-end power sector services including project development, engineering, O&M, digital solutions, performance auditing, diagnostics and training, serving prestigious clients at national and international level with innovation and excellence. Safety and sustainability are embedded in every step at STEAG. From customized decarbonization strategies like CCUS, green hydrogen mission and methanol economy, we deliver performance that aligns with the emerging energy vision. With a digital-first approach, STEAG leverages advanced tools such as Epsilon, Pardo, Power Factory, CMS, incorporating thermodynamics and AI/ML models to transform plant data into actionable insights, enhancing reliability, availability and cost optimization for customer delight. Internationally reputed STEAG Learning Center is recognized by CEA, Government of India, for customized and high-quality learning experiences, encompassing classroom training with modern simulator and field exposure. STEAG India, powering performance, inspiring trust. Partner with STEAG for a brighter future where reliability meets innovation.
This session is regarding best practices for efficiency enhancement in coal-based power plants. Coal-based power plant operation maintenance is a very complex system, and you must be doing this day in day out. But knowingly, unknowingly, we do slot-running deviations, which reduces affects our efficiency of the power plant. So I will take you through next 3 years through various systems practices which are supposed to be best in the power plant operation and maintenance. So why we need a best practices? This is our presentation agenda, learning agenda. Importance of best practices, plant efficiency and what is its significance, then boiler performance analysis and optimizing measures, boiler combustion optimization, best practices for efficient heat transfer of boiler pressure parts, air preheater performance enhancement, turbine cycle efficiency analysis and best practices for improvement, condenser performance monitoring and improvement, feed water heater performance enhancement, cooling tower performance enhancement, DM makeup and auxiliary power consumption reduction discussion, and we will have subsequently, as Madam said, intermediate discussion and concluding discussions. So these are the main components identified for the efficiency of the power plant. So I'll take you through one by one. First, let us introduce ourselves to why we need a best practice in a power plant. You know, power plant, as already I told, complex system and very costly assets in the power plant. And without having best efficiency out of each and every equipment, we will not be cost competitive. You know what is the present per megawatt installation cost? It's running around 9 crores per megawatt for a conventional thermal plant power plant of supercritical, ultra supercritical units. So you can imagine the fixed cost, and then the coal is also very costly, costly product. So once we combination of these two, energy charge rate will be very high, and then even fixed cost will be very high. Unless we be cost competitive, we cannot stand in the market. The days are going to come in India that each consumer like you and me, can source our power from the cheapest from anywhere in corner in India. So that type of market is emerging slowly and slowly. So we need to be cost competitive. Otherwise, we cannot stand in the market. So this one of the reason of to be best is cost competitiveness. Then you must be knowing already. You are a power plant engineers. Nowadays, the environmental norms have become stringent, more and more stringent environmental norms. Even particulate emission, now the limit is 30. Even SOx limit, it is very stringent. That's why people are introducing FGDs also, NOx burners also we are introducing. So everything is very, very stringent environmental conditions are being proclaimed. Hence, we need to be best operating power plants, best practices needs to be there in the power plant to meet all these environmental norms. Then you appreciate the fact that coal is a very precious resource, coal, oil, whatever it may be, very precious resource, which is a limited resource is available. So we need to conserve these resources. And as power plant goes on operating under very high adverse conditions, high pressure, temperature conditions, there will be aging factor also. And presently, because of introduction of RE into the system in the day hours, there is a load reduction schedules are minimum in the morning hours. In the evening hours, it is picking up. This type of flexibilization of the operation has introduced severe stress on the power plant equipment. So we need to be upgrade ourselves and have the practices, systems in place to meet these challenges. So best operation maintenance plan can improve, sustain the plant performance. So it requires continuous efforts to maintain status, and even more efforts required to make improvements. So I'll take you the next. What is efficiency? What is efficiency? You all know from the childhood we are reading, it is output by input. How much output we are getting for the given input. So in the power plant context, if heat rate is the more predominant indicator of the power plant efficiency, it is nothing but heat required in kilocalorie or kilojoules to generate a kilowatt hour of power. That means 1 unit of power, it is expressed as kilocalories per kilowatt hour or kilojoules per kilowatt hour. This is the most representative parameter of a power plant efficiency. Unit heat rate is, you can see, heat input to cycle in kilocalorie. That is fuel burn, that is kg of fuel burn into calorific value of the fuel divided by power generated in kilowatt hour. This is the unit heat rate. That means fuel is input is in boiler, power output is a generator, and entire cycle is covered. Now coming to turbine cycle heat rate, it is gross turbine cycle heat rate is heat input of the turbine cycle. That means through main steam and hot reheat, how much heat is input. Then what is the power generated at generator terminals. Now heat and efficiency both are inverse, have the inverse relations. Efficiency is equal to 860 into 100 by heat rate. This 860 component has come from the Carnot cycle, which is the best cycle for power plant operation. So 860 into 100 divided by heat rate gives the efficiency of the operating efficiency of the power plant. Now in general, we always talk in the heat rate terms. So factors affecting the heat rate and efficiency of the unit are basic design aspects. It is a design feature. That means how the plant is designed, what is the parameter set in. Suppose you just take this normal conventional subcritical boiler and supercritical technology. There is a vast difference in the heat rates, vast difference in the efficiencies. Higher the pressure temperatures, we will get the more efficiency. Nowadays, the materials are available, so people are touching the 600 plus, and pressures are also 285 something. So what I mean to say is, it is a design aspect also decides the basic heat rate of the power plants. Then machine rating, as I already covered this. Ambient conditions, under what conditions this is a plant is operating, very hot conditions, very cold conditions, all these things decide, and relative humidity. Ambient conditions decide, also have the influence on the efficiency or heat rate of the power plant. Condenser vacuum and partial loading, definitely partial loading, there will be heat rate deviation, because the units are designed for base load. Once you go for the partial load operation, there will be deviation in the heat rate. So I'm not going into the details of compensations and all, but the partial load operation has bearing on the efficiency. Then coal quality is a direct bearing on the boiler efficiency. Aging of the turbine, aging of the components. Chemistry also has, it affects the heat transfer of the various, either in condenser and boiler, or other components, heat transfer components. Chemistry has a bearing. Lack of awareness and knowledge, because this is what our aim is today also, because day in day out we must be operating power plant, and unknowingly we must be doing some deviations which are affecting our efficiency. So knowledge is most important, awareness is most important, for one of the major factor for improving the efficiency. Now, any parameter has to have a comparison for evaluation or gap analysis, whatever you say. So what is the parameter which can take, what are the reference values we can take for the gap analysis or comparison purpose? Either it can be design parameters or performance guarantee test parameters. Of course, design parameters, it may be certain parameters can be achieved, certain ambient conditions we don't have any control on them. So design parameters, achieving design parameters may be a difficult task, but the best thing would be the parameters and performance achieved in the PG test. PG test is conducted in the controlled environment. I think you must be knowing, because we do the cycle isolation, there will not be any makeup, there will not be any soot blowing. Soot blowing is done prior to 2 hours, 4 hours prior to the efficiency testing. Then there will not be any de-ashing during this. So no cycle is completely isolated, and performance test is conducted. These results we can have the PG test results we can have used as a comparison for the gap analysis purpose. And one more thing, important thing for the gap analysis and awareness, I can say, is the plant personnel should have the impact of deviation in the financial terms. That means 1 degree of main steam temperature, how many, that depends on plant to plant. Plant personnel have to evaluate and calculate and see how much deviation, how much influence of the financial terms. But in general, what are the parameters you list out, and what is the financial impact on the deviation in these parameters? We can display at various places, locations, so that each plant personnel will have that awareness and try to minimize whatever best they can do within the circumstances. Now, I'll take you to the second, this thing, boiler efficiency. Now, what is boiler efficiency? Boiler efficiency is evaluated in 2 methods. One is direct method. Direct method is nothing but the heat added to the steam in the boiler and into steam flow by GCV of heat output by input. So GCV of fuel and coal flow. But this method is not widely practiced because there are measurement errors. So many measurements errors will be introduced in this, like coal flow. Coal flow measurement is not that accurate. Then steam flow measurement at that high temperature and pressure have higher errors. Now, because of this errors in the calculation of this methodology, generally boiler efficiency is calculated through heat loss method. Heat loss method is nothing but heat 100% minus losses plus credits. This is the methodology they use. 100%. That means efficiency 100% if you take, out of which losses components are taken out, like dry flue gas loss, moisture in coal and moisture hydrogen in coal, moisture in air, unburned carbon monoxide formation, sensible heats in ash, radiation, uncontrolled unaccounted losses. All these summation of these losses, these are the major components. Summation of losses are subtracted from 100%. Plus, there are some credits to be added in the boiler efficiency. What are the credits? Like if you take the cycle isolation cycle, entire boiler cycle up to fans are also included in the cycle, then the credits will not be there. Otherwise, if you take aerator outlet, up to aerator outlet, the isolation is taken, then the fan power, mill power are also added as a credit because they are putting some energy into the air. So that the air and coal, so that is also added as a credit. So with this methodology, the generally calculated. I will not go into the details of calculation, that is efficiency testing part, but general idea I'm giving. This is the methodology we follow. Then above losses, all the losses around 12.5 to 15% they account for. That means boiler efficiency could be somewhere around 87.5 to 85.5, something like that. So, but general, it is for subbituminous coals, boiler efficiency is around 87%. Generally, it is 87 plus. Now, these are some losses are controllable in this, some losses are uncontrollable. We cannot do anything on that. Like dry flue gas loss is a controllable loss. Then unburned carbon loss is a controllable loss. CO formation losses is a controllable loss. Rest of the things, radiation and accounted losses are right from design stage. It is their best. The insulation will give the radiation losses minimum. Then hydrogen and moisture in the coal we cannot control. Moisture in air we cannot control. So there are controllable losses. There are uncontrollable losses. So we will concentrate on the controllable losses. Suppose if you take influence on a CFBC boiler, just like that, I'm just touching that. In a CFBC boiler, the generally lignite, suppose if you use a lignite. In lignite, moisture will be very high. So that losses components will be very high in lignite operated plant. Like that, each component has got different bearing on the design of the boiler and efficiency of the boiler. Now, what are the measures we can adopt for efficiency enhancement? One is boiler combustion optimization, boiler pressure pot heat transfer improvement, air filter efficiency enhancement. All the factors which I was discussing about the controllable losses are covered under this, under three major components. Now, what is the calorific value? Just I will touch upon few words on this calorific value. That is heat content per unit of coal expressed as kilocalories per kg or kilojoules per kg. So coal is a complex compound. Once you burn the coal, it has got carbon, it has got volatile matter, it has got moisture, it has got ash also. And this, once we burn, it releases heat. That heat is called as calorific value. You have GCV or HHV. There are two ways we can express them. GCV or higher heat value, gross calorific value or higher heat value. It is the total amount of heat produced when a fuel is burned, completely burned, and combustion products are cooled to the initial temperature of the fuel. It means the moisture inside the coal gets evaporated and it has absorbs the latent heat for evaporation. That heat is released to the net heat. So that is then product is cooled, water is condensed. So then it is called GCV. The total higher amount of heat will be available for use. That is GCV. Whereas low heat value is we cannot condense. We cannot the water vapor produced during combustion is not condensed. So latent heat is lost. So that is lower heat value. So calorific value is a necessary measurement for basic measurement for the boiler efficiency calculation, and it is also required for fuel payments, coal payments. It is all coal payments are done based on This only the you must be aware that coal is divided into several grades. Now G17 up to G1 to G17 Indian context. So bituminous and anthracite bitumen, all the coal are divided into G7 up to G17 grades. So the payment of the for the coal to coal companies depend upon the GCV of the of the coal. So as I already touched, the proximate analysis, the coal analysis is done in two ways. One is proximate analysis, which is more readily can do in our laboratories: moisture, ash, VM, and fixed carbon. Whereas ultimate analysis, element analysis, it can be done normally. Generally, plants do not have this capability. Some plants may be having, but generally this it is done in the laboratory. It takes a lot of time, and we have to go approach either say CMRI or CFRI, Dhanbad, coal companies, laboratories, and even IITs like that for getting this analysis. So, but once you have proximate analysis, you can convert that into ultimate analysis through a empirical formula. That through empirical formula we can convert that and go for our analysis purpose, regular analysis purpose. But for PG test purposes, I'm repeating this, PG test purposes, the proximate analysis, ultimate analysis, proximate analysis, the moisture can be done in our laboratory, both the parties agree, but ultimate analysis is done in a enable accredited third party laboratory to have the independence, because it has a contractual obligation. It is not done through formula based. For regular purpose, day-to-day, our analysis purpose, we can use that formula, which for trending purpose, that can be used. So influence of various components in the boiler combustion. Volatile matter. What is the influence of volatile matter on combustion? So the volatile matter actually limits the pulverizer outlet temperature and fineness requirement. Because pulverizer outlet temperature, normally we pulverize the coal in the pulverizer and we preheat this fuel and send to the boiler. So normal general subbituminous coals we keep around 80-85 degrees centigrade, 80-85 degrees centigrade if VM is low. If VM is high, then there is a limitation on the mill outlet temperature. It may be around 65 degrees centigrade only. Similarly, volatile matter has influence on burner and air damper settings, ignition for combustion, flame stability also. High voltage VM coals will have higher flame stability. Low VM coals, there is a chances of flame failures, furnace trippings and flame failures, because low VM has got sustenance on the combustion will be low. Then burnout carbon content in fly ash. And then moisture has an influence. Each moisture has got two types. One is surface moisture. That means the coal, it is external moisture. The moisture in the capillaries of the coal particle is the surface moisture, which can be easily taken out during heating. But inherent moisture is in a compounded form, which will not come out due to heating and all. It has to be burnt out. So these are the two types of moistures. High moisture will reduce the mill capacity, because we have to maintain the outlet temperature of the mill. High moisture content will, high moisture coal will have low outlet temperature. So mill loading has to be reduced to maintain the outlet temperature. And it also lowers the thermal efficiency, because high moisture will carry away more heat, in the flue gases. So in the form of vapor. So that is also lowers the thermal efficiency, and moisture increases the flue gas volume, because the 1 kg of if you take liquid and it is 8 times volume has increased, so it will increase the ID fan loading, aerator performance also. Now, influence of ash. Ash is a waste product not in that context. Ash nowadays has got a lot of uses. Now, I'm not talking about in that context. I am talking about the combustion part of it. So ash doesn't burn. Ash is incombustible residue of a combustion. So it is a burden for us, because if you take Indian coal has got around 40 to 44% of ash. Suppose if any power plant gets 10 rakes, You can just imagine you are carrying ash in 4 rakes, 4.4 rakes, or for 40%. If you take it is 4 rakes, it is coming as ash. So this much ash we are transporting from the mines and bringing it here, handling it, then loading into the boiler, burning coal, then that ash comes out and we have to dispose it. So this is a sort of pain for power plant operators, because ash disposal, ash utilization is our prime responsibility, one of our prime responsibilities. The polluter will pay. That is the motto now. We are the polluters. We have to pay for that. That means either it has to be utilized either in mines backfilling, or road construction, or brick manufacturing, or gypsum, or various utilities, I can say. But mines backfilling also it can be used. So this is the ash doesn't have add any value to our combustion process. But role of ash is, as I have already touched all these parameters, it also influences your flame stability, combustion, boiler efficiency, clinkering, slagging in if fusion temperature is less, impacts ESP performance, high ash content, ESP doesn't function properly, increases coal requirement for the same load, all these things listed out. Erosion, one of the major mechanical problems in the ash is it is a highly erosive component, and it will erode away the boiler tubes. Boiler maintenance engineers will appreciate this point, because they in and day out they see economizer or water walls, water, or even a second pass components. There is a severe ducts also erosion will be there. And if you have anybody from CFBC boilers, they can appreciate this point. You can see the bed ash. CFBC boilers, ash is circulated inside the combustor along with the fuel. It is a bed material which is circulated from combustor to cyclone back to boiler. So the erosion pattern, because erosion pattern of this bed ash of the combustor water walls is severe. We lose millimeters in some time. That's why several techniques are available right now. Metal spray coating, tungsten coating, to high abrasive resistant coatings are available, which power plants are adopting for reduction of this erosion. Then fixed carbon. Fixed carbon is a combustible fuel left in furnace after volatile matter burns off. That means actually this is the heat giving product material. It is calculated as 100 minus moisture plus volatile matter and ash. Moisture is evaluated in the coal, volatile matter is evaluated, then ash is evaluated, rest is your fixed carbon. The higher the fixed carbon, higher the GCV. Low fixed carbon, lower will be the GCV. Sulfur, what is the influence of sulfur? It is not a component which is expressed generally in the proximate analysis. However, it has a bearing on the clinkering and slagging tendency of the coal. That's why I touched upon here. Corrosion of air preheaters, because high sulfur content means formation of SOx products, and that aerator exit flue gas temperature is limited. We cannot go below 125 degrees, 130 degrees. Then that will be higher loss in the dry flue gas. If you go below, that will corrode the downstream equipment like ESP, ducts, all ducts, even ESP component, ESP walls, then even ID fan ducts also. So it also lowers the boiler efficiency by limiting exit flue gas temperature, because higher flue gas temperature we have to lose, so it has bearing on dry flue gas loss. And stringent norms in SOx emissions nowadays. So that's why it is warranting upon necessitating to install FGDs. And I don't know how many people have got exposure to the FGDs. FGDs are now being installed. Several plants have installed FGD and they're operating. The end product is gypsum, which adds to the circular economy. That means we can sell gypsum. Gypsum has high demand for in the cement industry, and we get some income from the gypsum. But however, it is a capital intensive equipment. Earlier 2017-16 on at that time it was around 0.4 lakhs to 0.4 crores per 0.445 crores per megawatt. Nowadays it has crossed 1+, 1.1, 1.2 also it is touching. Some areas it is maybe it's little higher also. So that is adding to, and it adds to, FGD adds to auxiliary power consumption also. It adds to It adds to auxiliary power consumption, and of course, regulations now, CRC regulations, all regulations are incorporating this influence on the FGD. ECR also increases. In general, 500 megawatt, it is increasing by operating cost is increasing by 0.27 paisa on each kilowatt hour, 0.2 on each unit. It is has influence. So all these things have to be these are negative aspects of sulfur. Earlier we did not have this type of this thing. Chimney height was defined. Chimney height used to be 275 meters. Then we can discharge into the atmosphere. But now it is not. It is not allowed. You have to limit the SOx to. If you are somebody interested, I can just read up the latest norms for units which are commissioned after 2017. The particulate emission is 30 milligrams per nm cube. SOx is 100 milligrams per nm cube. NOx is also similar level, and there is no restriction on mercury also. So that also to be seen. Now I'll be back onto the discussion. Now, what are we were talking about the combustion optimization, combustion efficiency. So there are three major three T's of combustion, we call it as three T's of combustion. One is temperature, turbulence, and time. Just I'll spend some time on this. The temperature is the temperature at which fuel enters into the boiler, and it has to reach up to its self-ignition temperature and catch fire and release heat. So what we do in generally in our boilers, we this aids in self-sustenance of the combustion. What we do, we pulverize coal, we remove the moisture, and we carry this preheated coal to the burner. It sprays into the furnace. There already flame is available. The coal particle gets heated up to that ignition temperature. Meanwhile, volatile matter burns. Then it gives further heat, and the coal particle catches fire, and it starts burning, and it cools off after completion of combustion. So this is the temperature of the fuel which is entering into the boiler, and which is the ignition temperature, we call it as. Then turbulence. Each coal particle, after it catches fire, the surface is covered with the products of combustion. Surface is covered, I'm repeating, the surface is covered with the products of combustion. These products of combustion will cool off or prevent the further fresh particle exposure to the furnace, the flame, you can say. So there is a bad combustion takes place, and we lose unburned carbon in the bottom ash and fly ash. The turbulence is created by the air inside the we are sending into the furnace, primary air and secondary air. The turbulence creates removes the products of combustion from coal particle on the from the surface of the coal particle, and it allows always fresh char to be exposed to the conditions there, so that the combustion will be self-sustaining. So this is one of the major parameter, turbulence. Then time. The time for which the particle is retained in the combustion is also very important. It is a design feature, depends on air velocity, boiler volumes. So if you don't give the time, the whole unburned carbon will escape, heat will not be released, and we will lose more coal. The time has to be given for the particle to stay in combustion and to burn completely. So these are the three factors: temperature, turbulence, and time. I'll just touch upon this. This the coal burning profile, you can, if you see, it is the temperature, volatile ignition temperature where combustion of volatile matter just sets in. That means what I told you earlier. Once it gets into the furnace, we send the coal plus air in around 85 degrees centigrade, 90 degrees centigrade, depending on the conditions. From there, it starts picking up heat inside the furnace for the prevailing flame conditions there, and the temperature reaches to 200 plus there. Then it starts burning. Then it is called the volatile matter. Just for combustion of volatile matter just sets in. Then next is ignition temperature, where ignition of char takes place. That means coal particles start taking place. And the PT is the peak temperature where the rate of heat release is maximum due to char combustion. BT is the burnout temperature where burning of coal is complete and exothermic heat release becomes zero. That means further nothing is left in the char particle. These temperatures gives indication of the possible delayed combustion. If you see the profile, if you see this profile, it will give an indication that possible delayed combustion of the type of coal. So this is one of the very important aspects to be seen. So if you want boiler, you don't have much choice on the types of coals. If you want to burn different types of coal in the together, then you should have the burning profiles. Almost similar burning profiles have to be compared, and then the coal as a blended product can be used. So these things have to be important. Seen profile has to be understood. Profile has to be analyzed. Then different coals having similar profiles will be best compatible for the blending purpose. So my entire discussion on the combustion optimization revolves around that three components: time, turbulence, and temperature. These three components we will be concentrating in one form or other. So what is the influence of coal fineness on combustion optimization? Higher surface area per unit mass of coal. This is self-explanatory. If you crush coal into small, you know what is the pulverizer limits, you must be knowing. The 200 mesh more than 70%, less than 50, retention in 50%, less than 0.5%. So is coal is almost crushed to a talcum powder level, you can say. That gives each particle, because of this pulverization, you have more surface area, and more surface area means more exposure to the conditions inside the combustion, and you can burn the coal with lesser amount of excess air because of this exposure, increased surface area. And higher combustion efficiency we can achieve because particle size is so small that it burns rapidly and completely, so that lower we can reduce the unburnt carbon in ash. Then higher heat release per unit mass, fast response to the load changes, because pulverizer fuel boilers compared to, I can just touch upon the CFBC boiler here. The CFBC boiler response time for the load fluctuation is a little slow compared to pulverizer fuel boilers. No doubt, stability aspect, CFBC may be having better stability under similar conditions, but the load response, suppose the ramp rates and all, it is very difficult to achieve the nowadays recommended 2 to 3% ramp rate in a CFBC boiler because of the intense heat stored in the refractories and the bed material. The response is very slow. But in pulverizer fuel boilers, it is faster. And this pulverization in coal fineness allows us to burn wide variety of coal, because Indian coals, we have different varieties. Each plant must be sourcing coal from different mines, different sources, even including import coal. So wide variety of coal can be burned, and low volatile matter to high volatile matter bituminous coals can be burned. Low grade coal to high ash content coals also can be burned. And the fineness reduces the fan power also, because of it can easily burn out with less amount of excess air. It can be easily burnt because of pulverization. It can be easily burnt along with oil or gas, in combination of oil and gas. Then we must be talking about excess air, stoichiometric air. We will touch upon these two aspects. But the theoretical air required for complete combustion of coal is fuel is stoichiometric air. The stoichiometric air allows the complete combustion of the fuel particle. However, for complete combustion, we maybe have to require little more air because of the prevailing conditions and different deviations in the conditions in the boiler. So complete combustion results into carbon conversion to carbon monoxide. Instead of, it will not allow the carbon formation of carbon monoxide, hydrogen conversion to water. The theoretical equation is you're able to see 2.67 kg of carbon plus 8 kg of hydrogen and 1 kg of sulfur and oxygen available in the fuel. This is the stoichiometric airflow equation. Theoretical air required will be because oxygen by weight is 23.2% in the air. So the theoretical required is divided by 23.2. Stoichiometric air is required for complete combustion. However, under the practical situations, additional air is required for completing the combustion, because the reasons being lack of perfect mixing between fuel and air, fluctuations in fuel flow, because the coal plus air is not a homogeneous mixture going through the pipes, coal pipes. It is a heterogeneous mixture. So there could be some variation in fuel flow, variation in calorific value of coal. Nowadays, okay, we say that this particular mine has this calorific value, but each bed has got different calorific value. So there will be changes in calorific value because of its heterogeneity. And controlling the one aspect here I would like to stress is, as per classical thermodynamics, Van Wylen, you can refer to that textbook, Classical Thermodynamics by Van Wylen. In that book, it is the combustion equations are elaborately discussed, and the stoichiometric air requirement and excess air requirement. What is the influence of excess air requirement is elaborately discussed. If we burn the fuel, if we burn fuel with correct amount of stoichiometric ratio under very controlled conditions, the temperatures are very, very high than what we achieve in the boiler. Suppose if it is the boilers, we are achieving with excess air combustion temperatures of maybe 1200 to 1400 degrees centigrade, it will be at least 1.5 times than that. It will be very, very high. So the excess air cools the combustion also. That also required, because we cannot we cannot sustain that temperature inside the furnaces. So that is also required. So controlling the combustion temperature exercise is required. Formation of CO is drastically reduced, because incomplete combustion leads to formation of CO. CO is complete heat is not released. CO2 is maximum heat is released. Formation of CO reduces the release of heat. So excess air is must, and depends upon the design, depends upon the practical O&M experience. We can decide upon the excess air. However, supply of more excess air than required decreases the boiler efficiency, because it carries away heat in the dry flue gas form. It cools off the combustion. It doesn't allow complete release of heat. That is also one of the negative aspects. Excess air required at part load will be higher than full load, because of the lean air fuel mixture. Now I'll go to excess air deviation possible reasons, because boiler is almost operations are controlled operations, and it is mostly automated operations. So in the automation, there may be problem in fuel air flow control, fuel poor mill fineness. This could be one of the reason, and air ingress to the boiler. This could be one of the reason. Excess air deviation I am talking about. Burner malfunctions could be there. Then FD fan inlet vane mispositioning. It may be not operating properly. O2 values at economizer outlet is not representative. Normally, we measure oxygen at the economizer outlet. That may not be representative. So we are because if it is not representative, what we will do? We will supply excess air which is different from that than required. So this is automatic control. From that it senses, and it will supply a different percentage of air, excess air. Now the corrective actions, you can imagine from the problems, corrective actions are visible. Inlet weight position we need to attend. Then opportunity inspection of the appropriate burners maintenance. We have to, each shutdown you have to, if it is a longer shutdown, you have to, longer shutdown means if the temperature inside the boiler is conducive for entry, you should inspect the burners, because it is one of the major problem in power plant. The burner, either eroded burner or burner heads not aligned with the burner tilt position, like that. And there may be some honeycomb formation on the furnace mouth, burner mouth. So we need to inspect and attend to those problems. And in major maintenance, of course, burner replacement or repair has to be taken out, carried out. And air leakages, we will discuss in detail in subsequent slides. Air leakage is a cancer, I can say. Air leakage into the furnace is a cancer. What it has effect is it cools off my furnace. Second point is I am not able to supply air where it is required. My ID fans are getting loaded, and air preheater is also heat transfer is affected, and air heater exit gas temperatures are low, but resulting in some other consequences. So all these things, air leakage is very bad into the furnace. And fuel air control loop hardware calibration has to be checked. Classifier vane adjustment, this is for fineness of the coal. Condition based replacement and replacement are polarized internals, because worn out internals will not give proper fineness, which is a great loss to the efficiency. If you curtail to get the maximum benefit, if you curtail the excess air, it will formation of CO may be there, which is also a loss. So you have to optimize between O2, excess air, and the CO. Combination of both are now being used for optimization of air. So you bring down the excess air to that limit where just CO formation starts showing up. Maybe single digits, maybe 10, 15, around 10, you can say. So that optimum optimization needs to be achieved. That is a practical day-to-day affair. We need to adjust, because it depends on the coal quality, it depends upon the furnace conditions, it depends upon various other influence parameters that boiler operator has to adjust or fine-tune the excess air and CO in combination. A combo of these two has to be adopted. And one major point in oxygen, I was talking about the oxygen may not be representative. One major point is we place oxygen probe at economizer inlet, air heater outlet, or even ducts downstream the air preheater, but the positioning may not be appropriate because the positioning gives me the entire control on the airflow into the boiler. So the positioning and the most representative location we have to select for positioning of O2 probe. Most representative point is how to achieve this most representative point. So you have the multi-grid concept, measure the oxygen at various locations. I can see the diagram also across the duct. Across the duct at various positions, you measure the oxygen, average it out, and select a position where this average is very close to the measured value. That position represents the correct position of the O2. That needs to be done, which will resolve majority of the excess air issues. That needs to be done. That means, I will repeat once again, you map the duct, air preheater inlet duct, and then measure at various across the duct. You have to form a grid. I have just shown 4. It may be more, it may be less also. So I have shown 5 locations at three positions. That means 15 locations. It may be 20, it may be 25, depending on the duct sizing. So that needs to be carried out. Each position you measure the oxygen percentage, average it out, and the average value you compare with the measured value. There will be one location where it is exactly nearly very close to the measured value. That position you have to place the oxygen probe. Now, retention time in the furnace. As I already touched upon this, adequate time is needed for combustion reaction to completing furnace with ignition energy available to the fuel air mixture. Retention time required depends on fuel type and quality. If fuel is hard to burn, then it requires more time, like anthracites or super grade upper bituminous coals. And if fuel has got high VM, it will burn faster because VM is there to increase the temperature in a quicker manner, and it burns faster. Second is fuel fineness, furnace size. Furnace size is also one of the influencing factor because it's a design feature, you can say. Fuel air and fuel flue gas velocity is also design feature for under the given circumstances. However, it varies with the parameters. Like what I mean to say, suppose you maintain the design PA flow, design coal flow, design secondary air flow, then it will be very close to the it is a design values. However, if I pump in more air, if I pump in more coal, the velocities across the furnace will change, and it will be either high, it will be more or it will be less. So that partly depends on design, partly depends. And if you pump in more air and higher fuel velocities, higher velocities inside the furnace, it carries away it carries away the fuel to the second pass. It leads to secondary combustion, where if some air is available there, secondary combustion, or it carries away unburnt into the fly ash. And if coal is hard to burn, it is carried a carbon, unburnt carbon in bottom ash. It will we will lose unburnt carbon in bottom ash. So we need to optimize the air flows, fuel flows into the furnace, which will control these velocities and control the combustion and retain the combustion chamber. Then furnace draft is one of the influencing factor. One best practice is to optimize PA header pressure and PA flow through each mill to the extent minimum possible to optimize the furnace draft and optimize the furnace draft. This will help in little way as to some extent the controlling of the time of retention in the furnace. Then I'll touch upon primary airflow. To primary airflow optimization is must, because ignition instability, higher primary airflow, ignition, there will be unstable ignition, and to avoid carryover of coarser particles from the mill to furnace, because high pressure, high velocity, higher quantity of primary airflow will carry away, will disturb the fineness of the polarizer and carry away the coarser particles with might into the furnace. So this needs to be avoided. Primary air optimization is required to avoid settling in the coal pipes. If you reduce the flow to that to very low values, it will allow the coal particles to settle and leads to coal pipe choking. So it is required for uniform coal flow, also required in the four corners of the mill, for which this primary flow is also very important. So coal pipe temperature and mill to furnace DP measurement are a good indicator for coal pipe choking, because if coal pipe temperature monitoring is available in the control room, the boiler operator can see the coal pipe temperature continuously, and then he can raise the alarm if temperature is falling. So that, and mill to furnace DP, this is also important, because if coal pipes are choking, mill to furnace DP is a clear indicator that something is wrong with the either pipe choking or something is wrong with the mill. Then some indication about the mill reject also. From mill reject also we can have some indication of the coal pipe choking. One is fine reject. If you are getting very fine reject, fine particles are escaping to the mill reject, then we need to check up the coal pipes. That is one of the indicator. So we have best practice already I told, You install thermocouples or RTDs on the coal pipes and start measuring if it is not available. And you can contract some supplier who will install the pads and give you the RTDs or thermocouples, which can be installed on the coal pipes, so that the choking can be monitored. Tendency of choking can be forward. PA flow to be adjusted, coal flow as per the coal versus PA flow curve. This is a manufacturer's curve. According to that, we need to adjust the PA flow. So we discussed about it. Thumb rule is coal flow as a common sense. If the more the temperature of the fuel air into the furnace, my pain will be reduced to preheat the coal air mixture. But however, there is a limitation. It should not spontaneously ignite inside the coal pipes. So the general best operating temperatures are 80-85 degrees. To some extent, boiler operator can have the judgment around maybe 85 degrees approximately. And if it's a high VM coal, we need to control the temperature. So the thumb rule is 100 minus VM percentage is the maximum outlet temperature that is allowed for the thumb rule. This I'm telling thumb rule. So that can be taken. Okay. high VM coal, you need to restrict the coal mill outlet temperature as 60 to 65 degrees, and mill outlet temperature below 60 degrees may lead to settling in the pipes. So you need to strike a balance in between, depending on the quality of coal, VM, and this furnace requirement. So unbalance in the coal pipes. What happens? Unbalance in the coal pipes. It is having lot of bearing on the combustion characteristics, because non-uniform distribution of air fuel into the furnace. That is one primary, and turbulence gets disturbed, flame ball gets disturbed. That tangential fired boilers have the flame ball inside the furnace. That is also disturbed. Cylinder, you can say, that is disturbed. So we need to have more or less balanced air and fuel mixture through the coal pipes. That is for maintaining the balance. You all know that mills are situated at the ground floor, and all the four pipes are running through across around the boiler for all the four corners. Now each corner, each mill, depending on position to each corner, will have different length. Coal pipes to each corner from mill will have different length and will have different resistance. Hence, the flow simply cannot be uniform. So for which the mill manufacturers and boiler designers will recommend orifices inside the coal pipes. This will allow and ensure that the uniform distribution through pipes. Now, there are nowadays adjustable orifices are also available. So that is also one of the best technique for best solution for maintaining the coal flow through coal pipes, uniform coal flow. So the best practices is conducting clean air flow test, then conducting dirty air flow test. When we should conduct clean air flow and dirty air flow test? One is during boiler recommissioning after overhaul, after evidence of coal settling in coal pipes, by through monitoring or reject or flame disturbance, we can find out whether coal pipes are choked. If you touch the coal pipe, it will say. If mill is in operation, if you touch the coal pipe, it will say I am choked or I am not choked. But monitoring temperature is a good indicator. So poor coal fineness, high pressure, if it is fineness is disturbed, you have to carry clean air flow test. High pressure drop across the coal mill, excess mill spillage of the coal, and dirty air flow test also during boiler recommissioning after overhaul. It is slag. If any slag formation is observed around the burner of some mill, if CO imbalance across the furnace exit, the temperature unbalance at furnace exit, if large O2 spread there that means the combustion is not uniform, oxygen spread across the economizer is varied, very high variation. Then unburnt in the carbon, unburnt carbon in the ash, and poor flame appearance. If conditions prevailing, then you can choose to go for the airflow test. Just criteria for acceptance is coal pipe to pipe dirty airflow variation cannot be pipe to pipe variation cannot be more than 5%. Minimum dirty airflow velocity should be around 18, 17, 18 meters per second. Air fuel ratio to be 1.8 plus, but it should be less than 2.5. Minimum temperature, depending on the volatile matter, should be 60. Retention in 50 mesh should be less than as minimum as possible. But however, it consumes a lot of meal power. So preferably it should be 0.1 to 0.5%. And pass through from 200 mesh is minus 200 mesh is it is 70%. This is 70% is prescribed, but many plants are achieving 80 plus 85 plus also with required 0.5 less than 0.1 to 0.5. So you need to strike a balance. This friends, I have already told you in the initial itself, it is a continuous effort. Just theory cannot bring the best practices. It has a best practice only can be told, but it can be implemented by you people, and it's a continuous effort, I can say. Day in, day out, you have to practice all this. So it's a typical Indian coal and South African, just for comparison purpose. No bearing on that. You can see total moisture variation, total inherent moisture variation, GCV variation. So if you want to do some blending activity, you have to optimize. You can select. Suppose you are getting very poor coal, then you can select for a blending option also. Now, best practices for burning the different coals for optimum combustion. We have to maintain the mill exit temperature through cold air damper, 80 to 85 degrees for normal coal, low as 65 degrees for high VM coal. Fineness as already discussed. And coal fineness sampling, generally power plants do it with cyclone. However, if you can procure one isokinetic sampling probe, and it's not that costly compared to this thing. I don't have ready value with me to tell you about it, but you can procure. Once you procure a isokinetic sampler and do the sampling of the coal through isokinetic sampling, the results are best. You can come to the conclusion, a reliable conclusion, because cyclone sampler sometimes give a different value which we cannot conclude much. We will get confused unnecessarily. So better to use a isokinetic sampler, and coal sampling through isokinetic sampling can to be done. Means appropriate flow. We discussed boiler operator. If suppose I'm a boiler engineer, I'm operating my desk. If suppose I get this type of coal is fed into the bunker, and approximately after this much time it will come, it will have best indication for him that this can be done without any extra effort. What type of coal you are feeding, from which mine you are. If you have a data bank readily available, coal handling operator can convey a message, boss मैंने coal bunker C में ये coal डाल दिया, आपको present level is this, you may get this coal at after 4 hours. I have fed this coal from this mine which has got GCV like that. Such type of communication will also help the boiler engineers to optimize the parameters, but generally it doesn't happen. We after so many years of experience, we try to, but generally people don't bother to inform the control room people about this. Try to practice this; it will give good result. This I think we discussed coal mill pipe temperature once again. RFS adjustments can be done based on the conditions. Then SADC, yes, combustion optimization for firing different types of coals is optimization of SADC. General practical values I am sharing with you. If it is volatile matter is less than 20%, damper opening can be, fuel air damper opening can be reduced to 10 to 15%. For high VM coal, fuel air damper opening can be 30 to 35%. And auxiliary dam, uh, auxiliary dampers to be kept open at 50%. Overflow dampers based on the NOx values. Furnace to window DP generally recommended by the manufacturer, and it has to be judiciously maintained because it has got a lot of bearing on the combustion. If you do not maintain the furnace to windbox DP, it is generally what happens over a period of operation due to various leakages, dampers not in correct position. Outside you see dampers as 30%, but how inside it is either is wide open or it is fully closed. Like that, all sort of things will happen in the running units. So if you don't maintain the furnace to box DP, the flame containment in the boiler will be disturbed. Suppose if furnace to box DP is very low, the flame is enlarged. Overheating of the tubes may also take place. If it is too high, it may disturb the flame stability. So generally, it is around 100 mm of water column, 70 to 100 mm water column, but it depends on boiler to boiler. As per the manufacturers, you should go and try to attend to the problems as early as possible and maintain the furnace to window. You will see the results, wonderful results, flame stability, and even to the extent of overheating. Best practices: you have to check SADC position from local position indicator and control indicator on every shift. If not possible, at least once in a day, you have to see, you have to correct them. You will see really good results. You will get really good. These efforts will not go waste. And during opportunity, from inside the furnace, you have to see the secondary dampers position from the matching with the control room as well as the opening position as per the command, which will this will ensure you a stable combustion conditions, correct airflow admixture. This is we have discussed in this thing. Then, as I was touching upon the coal blending can be adopted. Of course, we cannot call this as blending. Basically, blending is actually a homogeneous mixture. Blended coal is a homogeneous mixture, but it is not possible to do blending to that extent. What we can do, we can have a good mixing. Though we call it as blending, it is a good mixing. So various wow, the selection of coal for blending. If your coal is poor, you need to select fuel for blending, which has got the similar burning profile, similar characteristics. So that will give you good mixing and better results. I think somebody has a question. Okay. We will discuss this in the break. Okay. You can lower your hand, my dear friend. We will discuss. Okay. Blending can be done through mixing using stacker reclaimer, or having higher coal quality coal in two bunkers or three bunkers. That also possible. So reclaim hoppers some plants will have reclaim hoppers. that also can be used. That means in reclaim hoppers, it is generally underground hoppers. Reclaim hopper, you feed other coal and better coal and normal coal at some intermediate junction point. You can mix them. I think I missed the slides. 1 second. So this slide we discussed. I think some people are joining very late. Maybe anyhow. Efficient heat transfer in boiler pressure parts. Now we were discussing the combustion optimization aspects. Now, if combustion is good but heat transfer is bad, then also results are same. We don't get it, desired results. So the indicators for the poor heat transfers are low steam temperatures, higher coal consumption, reheater spray for non high reheater and superheater spray for unwanted heat pickups. The location where heat is to be picked up is poor heat transfer. So the subsequent heat transfer surfaces we started picking up the heat. So that is also an indicator. Then higher economical outlet temperature, economizer outlet. This also is a good indicator for the poor heat transfer in the furnace. If the heat transfer takes place in the water walls, you get maximum steam generation for lesser coal file. Heat transfer has to be absorbed in the water wall. Rest of the thing is the dry steam goes into the superheater steam, reheater, or those sections with the flue gas convective heat transfers will help. But if heat transfer is poor, these are the indicators. Then the reasons could be ash, soot deposits, slagging, and fouling on the furnace walls or the heat transfer areas. Deposits inside the tubes, oxide film bhi ho sakta hai, or poor chemistry could be the one of the reason inside some scalings have taken place, which will result in repeated tube failures or due to overheating. And oxide over a period of operation, over a period of years of operation, exposure to the high temperatures, oxide film thickness can be formed, which needs to be either through replacement or through cleaning, chemical cleaning. We can get rid of them. And slagging and fouling is dependent on the ash characteristics because ash is a mineral composition which has got a fusion temperature, initial deformed temperature, and fusion temperature. It depends upon both of them. And ash base to acid ratio is also an index. Slagging and fouling index. So slagging refers to what? Slagging refers to formation of molten or partially fused ash deposits on the furnace walls, and surface is exposed to radiant heat. And in the radiant heat zones, slagging takes place. Fouling, on the other hand, is a formation of deposits on the convection heat transfer surfaces like superheaters, reheaters, often after the flue gas had exited the furnace. This is the basic, but both have the same effect. Both have the same effect. They inhibit the heat transfer. So it's only for theoretical purpose. I just wrote it down. The effect, our aim is to avoid slagging and depositions or fusions. Let us understand little bit about the ash fusion temperatures and initial deformation and fusion temperatures. That initial deformation temperature is the temperature at which ash starts softening and making onset of melting just before it just starts softening. If IDT is greater than temperature in the furnace, what happens? The ash particles will be dry. So they will not melt, soften. They bounce back into the stream and the flue gas, and it can be removed into by soot blowing. When IDT is less than temperature in the furnace, ash softens and sticks to the furnace walls. So that starts inhibiting the heat transfer. Ash fusion temperature is the temperature at which ash produced from burning coal or other solid fuels starts soften and melt. So ash melting takes place. Ash fusion temperature depends on composition of ash, and it is increased by presence of Ash fusion temperature is high for ash having higher silica and higher aluminum oxide. So that will be high, which is good. But high ash fusion temperature, ash is released into the furnace, will cool quickly to the non and it will not stick to the furnace walls. Whereas low ash fusion temperature results in ash will remain in molten state and causing the potential deposition on the furnace walls. Though ash characteristics and boiler design both are important factors for this slagging and fouling, but some of the operating pattern parameters will also control this, like air distribution, fuel distribution, coal fineness, excess air. These are also influencing to some extent. Air and fuel less than theoretical in some burners will give high temperature zones and localized reducing conditions and aggravating the slagging formations. Whereas high coal air ratio delays combustion and upset heat distribution, resulting elevated temperatures in upper furnace and leads to secondary combustion. Long burnout times increases potential of burning particles to contact furnace walls and heat transfer surfaces. So these are the parameters also to some extent influence, which we can control. How to minimize the best practices? You can say burner adjustments to avoid flame impingement on the walls, direct hitting on the furnace walls. It can be done by burner adjustments, coal flow balancing in each corner, maintaining furnace to windbox DP, which I was discussing earlier, maintaining pulverized fineness. Low fineness may cause delayed combustion because particle size is more, it takes more time to burn, and longer resistance times and may cause slagging in the lower furnace. Maintain excess air to minimize the conditions conducive for formation of localized reducing conditions in the furnace. And cold air velocity test can be done, proper velocity distribution across the boilers. Sometimes if you during the operation you may be observing that there are big lumps falling inside the bottom ash hopper. Lot of noise comes. That means that clinker formation. Clinker is a very bad word to use, but that large lumps are getting formed. In that condition, you can go for split mill combination. You have to break the milk split mill. If you use that, can be to some extent avoided. And soot blowing is a must, very best technique for dislodging the deposits and improving the heat transfer. Generally, soot blowing has to be done regular intervals. It's a preventive measure of deposition sticking to the furnace. It has to be removed. It can be removed only through soot blowing. That is the only technique you have right during the operation. Valve soot blowers, LRSBs, HRSBs are to be operated as per the predetermined frequency depending upon the experience. Valve soot blowers can be operated every day. If slagging is not there, you can operate once. Even small soot deposition on the furnace walls will also inhibit the heat transfer. So once in a day is minimum recommended. LRSB, generally 2 LRSBs, 3 LRSBs, depending upon the temperature gain in the reheater or superheater, depending upon the conditions, you do operate the LRSBs based on experience and practical observations and optimization. And you can clean the boiler. You can clean the boiler with jet cleaning, which every plant does during the overhauling. Build the scaffolding and do the jet cleaning with high pressure jet to dislodge all the depositions from the furnace surfaces, flatten superheater, radiant root assemblies during the overhauls. Now,
Sir, now the break time is, I think, 4 o'clock. So,
I think I did not even finish half. Okay. Sure. Can we break after 5 minutes? I'll discuss this air filter and
yeah. Okay.
Yeah, of course, this is a basic component. Everybody talks about air preheater performance, and during overall, it is a major component which is either cleaned or replacement of the basket, seal adjustment. It is the very, you can say, heart of the boiler efficiency. You can say, as per thumb rule, if 20 degrees exit temperature, flue gas temperature is high, you will lose boiler efficiency of 1%. You can calculate yourself 1% boiler efficiency loss. It runs into crores. So the performance indicators are air preheater seal leakage, which can be found out from measurement of O2 before air preheater, O2 after air preheater, and gas side efficiency, X ratio. These are the parameters which are calculated, and DP across air preheater, which can be seen directly in the furnace. In the boiler DCS. If it is it is given, the operator can regularly see it and observe what is the increase in DP, and it is also indicator for the choking of the air preheaters. So gas side efficiency it indicates how effectively the air preheater transfers heat from the flue gas to the combustion air. Higher gas side efficiency means heat is recovered from the flue gas. A maximum heat is recovered. Lower means heat transfer is poor. It indicates internal conditions of the air preheater. The definition is flue gas. It is calculated as flue gas inlet temperature to the air preheater and flue gas outlet temperature by flue gas inlet temperature to the air temperature. That means the maximum allowable margins available, that the on the denominator side and numerator side, what is the actual gain. So this way gas side efficiency is calculated. Deterioration of gas side efficiency indicates change in air or gas flow rate through air preheater, fouling on heat transfer surfaces, long-term corrosion of air heater heat transfer surfaces because of the high SOx contents or condensation at the cooler zones of the air preheaters. Best practices are use soot blowing as a technique of air preheater soot blowing regularly during the shift. If and during the startup, vigorously use every 2 hours you do the soot blowing, and during normal operation of the unit, every shift you should do the soot blowing of the air preheater. Monitoring and trending of the air and gas flow, pressure drops over the time to get idea of degree of air preheater choking. Periodic gas side efficiency X ratio calculation. These efficiencies departments to do, and it should be trended, and alarms should be raised for any deterioration. And basket inspection and seal inspection and adjustments during the opportunity and overhaulings. So seal leakage, the seal leakage, if seals are bad, what happens? Flue gas is at the lesser pressure, secondary air and primary air and higher pressure. There will be infiltration of secondary air and primary air onto the flue gas side. Once it happens, you are losing the quantum of air because of the infiltration, and flue gas at exit exit of air preheater gets cools off. However, if corrected air flue gas temperature is used, it will be much higher for the if a leakage is nullified. So the seal adjustment or seal perfectness is most important in the air preheater performance. There are nowadays online adjustment is available. If it is commissioned, use it and adjust the air preheater seals so that at least air ingress across the ducts. That means SA to flue gas, PA to flue gas is as minimal as possible. As minimal as possible. Just 1 or 2 slides more, we'll break. This is aerator leakage calculation. You can use carbon dioxide, you can use air at inlet outlet, and formulas are indicated. You must be people are well aware of these things. But if air leakage is there, air preheater performance deteriorates, boiler efficiency starts falling drastically, because The leakage increases the exit flue gas flow. That mass flow of the flue gas is more. ESP performance deteriorates. ID fan loading increases. It has the entire bearing on the draft system. Draft system is affected. So the seal leakage needs to be taken care appropriately with adequate maintenance interventions and proper operator monitoring and efficiency monitoring by efficiency department. So we discussed X ratio. A lower X ratio suggests X ratio is a parameter that proportion of heat transferred from hot flue gas to incoming air. So this is a parameter, a dimensionless parameter, which indicates how best heat is transferred from flue gas to the air, which is depends on the moisture, air leaks. That air infiltration is more, it will be affected. Air and gas flow rates. Lower X ratio indicates airflow is bypassing the air preheater. That means, suppose coal has got lower moisture, so mill outlet temperature is high. So you have to for controlling the mill outlet temperature, you need more colder air. So the primary air is, some part of the primary air is bypassing the air preheater and directly entering mill and going to furnace. This is tempering air we call. So that also has a bearing on the X ratio. If it is bypassing the air preheater, and relatively colder air is going to the furnace. And best practices are, you monitor the X ratio and gas rate efficiency by efficiency department and take the corrective actions as needed. Based on X ratio, you can tempering air can be optimized, and minimization of air bypassing the air preheater. Actually, any air entering into the boiler should, other than primary air, should enter through air preheater. Secondary air should enter through primary air. If air leaks are there, it is bypassing the furnace, air preheater. Somebody asked about the credits. Credits is nothing but, now we are asking for we are calculating the boiler efficiency through loss method. 100 minus losses we are calculating, but there are certain inputs going into the boiler as a energized conditions. Let us say, like air is pressurized in the secondary air and primary air and is sent into the furnace with energy input from the fans. So that has to be counted. That is a added energy input to the boiler, other than coal. Coal is also energy input to the boiler. Other than that, this is also an input. Similarly, mills also put in some energy into the coal. That is also energy input to the into the boiler. So that is also credit has to be added to the. So the total input going into the boiler, and what are the losses? The difference between these two we should account. Of course, for practical purposes, day-to-day affairs, somebody may omit the components of credit, but PG test purpose, credits are added. Then somebody asked a question. How windbox DP affects the flame length? Actually, basically, this is a flame containment I was talking about. Suppose furnace to windbox DP is lean, then flame enlargement takes place. If it is too high, flame disturbance takes place because of high pressure air impinging into the flame. So for a design furnace to windbox pressure, the flame profile is determined and pre-decided. But if any disturbance to these things will disturb the flame ball inside the furnace. And somebody asked what is the performance of online approximate analyzer. I cannot answer this question because practically some of the Indian coal context, some plants have incorporated, but I don't have right feedback. But in foreign countries, because the coal quality is uniform, it is some people are giving the indications that are working fine. But some of the plants they have introduced also. I can only say 50-50. I can say the feedbacks which I discussed is. But nowadays, some Indian manufacturers coming up with some non-radioactive type of proximate analyzer. So we need to see the performance and take the feedback from the power plants where it has been introduced. But it should work. It should work because um, uh, the advantage of online approximate analyzer would be because you have readily available the analysis part, because otherwise in the laboratory it will take almost 48 hours to get to the GCV values as well as the approximate analysis values. So it is good to have online approximate analyzer, but performance is not widely used. We are still on the conventional mode only, but slowly it is picking up. Let us see how it will work. Some people give the feedback they are working fine, but some plants maybe because of the local O&M conditions, local O&M practices may also be affecting this performance of the analyzer. So we let us wait and watch. And then may I know high temperature O2 sensors successfully running anywhere? They are running. Why they should run? Because the high velocity, high temperature probes, they have a cooling medium inside, so there will not be there is not any problem in this. Thumb rule for XSR. There is a curve for it. This thumb rule for XSR different load operations. This is the thumb. There is a specified curve for the boilers. General thumb rule is full load. Once what I will say, partial loading has got lot many factors influencing the parameters. What we talk the base load operations, 20% XSR, even 50 to 20%. What I was telling is you optimize the XSR percentage with the CO. Both have to be seen together. That will give the best XSR. However, the question is what is the thumb rule? The boiler manufacturer gives the curve. We can refer to the curve. That will give the correct picture. Cold. Is there in Thyssen CFBC cold cyclone boiler bed metal back shifting is observed? Sir, I think let us reserve this question. Sometime I will try to take up the CFBC class some other time, because it is purely related to operational aspect of the CFBC, which is not a right thing to be discussed here. We will discuss sometime later. I will take up a session on CFBC operations. That you can participate in that, and we can otherwise. If any possibility is there, I will note down this thing and revert back to you.